Okay. Let's continue from where we left and start with the pressure transmission coefficient. If we substitute for R here, we would have for minus R, 1 minus T. Or we can write this in a simpler fashion. Let's see, power expressions. Okay, this is the ratio of transmitted to incident pressure or transmission coefficient. Now let's take a look at the intensity and intensity reflection coefficient and intensity transmission coefficient. Remember, in the last unit, we described intensity for a plane wave in terms of sound pressure squared divided by rho and C. So when you define the intensity reflection, of course, you have intensity squared rho 1 C1 divided by reflection rho 1 C1, and that really pretty much gives you the same level or same coefficient as the pressure reflection coefficient. Okay, because the rho 1 C1 are the same. But when it comes to transmission coefficient. Okay. Then it's a little bit different because of the differences in the medium. You can see the difference actually is modified from the pressure coefficient ratio. It's modified now by zeta. So intensity is whereas reflection is okay. Now, let's talk about power. Reflection coefficient. Called R pi, pi for power. How do we relate power to pressure, to intensity? Power is intensity times surface area. And for plane waves, that would be p squared over rho c times the surface area. So in the case of a reflected wave, okay, in the case of a reflected wave, you can see that these areas, if you just consider these areas, they're the same. The angles are the same parallel lines go. So the areas are the same. So power reflection coefficient then will be simply the same as the intensity and same as the pressure. And that would be, what was our value, zeta? That's a power reflection coefficient. Transmission is another problem. Okay. Okay, transmission is another problem. This requires just a little attention from everybody. Waves come in, okay, just like we said, waves come in, they're reflected, the distance is the same, so essentially they maintain the area. But here, they come in and they change direction. So the lines are, of course, parallel, but by virtue of changing it, the distance between them is different. So you can have that as one area, S1 represent, and this is the other area, S2. Now, between these two triangles, the hypotenuse is common, okay? And let's see, this is the angle here, sine theta I, and let's see now, this, so I think, yes, this is the transmitted angle. So if you look at delta x being the hypotenuse, S1 sine theta I. Is that, am I just right? Yes. No. So, just a second now. I think it's cosine theta I. Yeah. This angle cosine theta I, and this would be S2 cosine theta t. So when you have this relationship S1 over S2, you can indeed write it as a ratio of the angles of incidence and transmission. Do you follow this? Is this clear? Yes, no, maybe? It's a kinematic relationship. Okay? The wave comes in here, it has a footprint on the interface. The same footprint now, okay, is giving you the transmitted wave. So what we're saying is this footprint is common to both of them, so we should be able to find the beam width, okay, for a respective area, because that's the amount of energy that's going through there. So going back and finding out what the transmitted power is. Okay, if you remember now, power transmitted will be intensity transmitted times the area of transmission. And power incident is incident intensity times incident area. Okay? And when we get the ratio, and make the appropriate substitutions, and what is ST? Okay, that would be cosine theta t cosine theta I. So and if one simplifies that further, this is not reflection, sorry, this is transmission. These mistakes. Okay, transmission. This is T, which we have from here. Let me simplify that a little bit. Okay. we have an expression for the transmission coefficient. Now, we can verify that the sum of the power transmission coefficient and power reflection coefficient add up to 1. But it's not the same if you try to do it for intensity. It's not the same if you try to do it with pressure. In other words, let me just write here to make sure that you understand. These are not correct. They will not hold up, okay? But this is, because this satisfies the energy conservation requirement, okay? You can check these results for yourself. Let's see now. Back here. Questions? Okay. Let me clean this up. Let's examine these expressions. Leave that there. Okay. Two expressions. One is how much acoustic power is reflected when sound comes at an angle. The other side may be another fluid medium. And how much sound is transmitted to the other side. Well, when you look at these expressions, usually you cannot help but wonder a few things. One of the things that I want to do is, for instance, I want to minimize the reflected sound. What can I do? How would you minimize the reflected sound energy? Not the amplitude or pressure, but energy. Okay, how do you do that? There are easier ways, but how do you do it? Yes? That's, no, because it will reflect. No, you have a given medium. No, don't look at it. It's not there. It's here. Look at the one thing that you need to learn on all the classes is read the equations, because there's a lot of stuff in there. There's a lot of information. Okay. Say again. And what happens then? All the sound goes through. Well, where does the, okay, if impedance is the same for both, okay, this is rho 2, C2, rho 1, C1 becomes 1. It is so obvious, that's why you're missing it. If you want to minimize the reflected, you make the numerator 0. What's wrong with that? And how does that happen? Now, we know that we can write cosine theta t in terms of a sine angle, right? See, if we have this relationship, then we have and we have to find out because you don't control theta t, but we are able to write theta t in terms of the incident angle. You remember that? Oh, that relationship. I see that. Okay, okay, that's all right. Fair enough. Okay, let's see now. We remember cosine theta t. We wrote in terms of 1 minus sine squared theta t, and that was written in terms of, let's see, C2, C1 over sine theta I squared. Okay, so if we put these values, substitute them. The angle theta I which makes is called the angle of intromission, and we write it as theta capital I. And this is then the condition for complete transmission. Condition for complete transmission. Okay. So if we take this just for a moment and we say for let's see now. Yes. Okay, we put it down there. Okay. This was the last piece on this in this development. Let's see now, anything else? Yes. Let me just go over this. Finish the derivation. I skipped a couple of steps, but they're not difficult. Okay. What we have done so far is, let me see if I have an example. We've covered the oblique wave problem in free field or in a field with only one boundary, okay? And in the second unit, we started the oblique waves incident on another fluid and how much sound is transmitted to the other side and how much is not. What you will see maybe several weeks later is when this boundary is not the surface of another fluid, but what if it's a structure? What happens? And here, if you push here, it only pushes at that point, meaning it's a locally reactive surface. When you have a fluid, you push it, it just goes down. Nothing really happens somewhere else as long as this is static. But if you have an elastic body, a plate, if you push here, you're going to feel somewhere else. So it is non-locally reactive. Okay? So if instead of the surface of another fluid or air, etc., now you have a structure and sound waves are incident on it, everything changes quite a bit. And the angle at which they are incident on the plate will make a big difference as to how much sound it will transmit to the other side. Okay, we'll cover that. So this angle of incidence, angle of transmission are very, very important. And the last thing we did here was take these power equations. We said, by the way, we did not say minimize reflected pressure. There is still a reflected pressure. Pressure has to be reflected. But we minimize, or we actually make zero, the reflected power. Okay? And that reflected power can be zero only if incident wave is at this value, determined by the ratios of the impedances and the ratio of their densities. That's it. It's quite interesting. Maybe not to you, but it should be. Okay? Let me run a quick another example problem. Another plane wave. Example. Plane wave in water. Actually in seawater, yeah. And sound incident on sand. You know, you do use sound waves to investigate what's under sand. It could be mines, bombs, but it could be also petroleum. It could be a number of different things. So, so this is not unusual. So for the sand, we have the properties: density, 2,000 kilograms per meter cube. Speed of sound, 2,000 meters per second. And seawater, has a density of almost 1,000 kilogram per meter cube, and speed of sound is about 1,500 meter per second. So the characteristic impedance is Pascal second per meter. So the questions that are asked: what is the reflected pressure? What is the transmitted pressure? And what's the power reflection coefficient? Okay, take a look and see what you can do. Erase this quickly. Well, you're supposed to solve this now. Can you do it? Normal incidence. Angle is 0. When it's not given, it's okay to assume, but it should be given. Normal incidence. You have these, right? And this is the pressure relationship, not power, not intensity, but pressure relationship. And what happens here? This is 1, because it's a normal incidence. So that's not a problem. Do you understand? Normal incidence, yeah, angle is 0, so they're both the same. And what are we asked? What is the pressure reflection? Well, as you know, you can find the reflection coefficient here. You can find transmission coefficient from here. And the reflection coefficient is, of course, PR over PI and PT over PI. Okay? I work on the homework problems. I think I will get you more examples so you can work on them yourselves, because I think that's the way you're going to become much more familiar with these. The next time we'll do some examples, but we're going to start on a new topic called waveguides. What waveguides is now, instead of sound propagating freely in a free field, we're going to see what happens when the sound is propagating in, let's say, between two surfaces. Then we'll look at what happens if it is a square cross-section, duct, or circular, and so on. But we'll start with two plane waves and how the sound propagates here. You would think that if you have a normal incidence, it's a piece of cake, and it is. It's very simple. You write the normal equations of motion, and there may be reflections, so you write that down, and so on. But what happens if the sound is a different direction? Okay? What happens, of course, is it reflects back, and so on. That is going to be very interesting, and we'll drive that equation and run some examples. The one key here is that you'll see sounds below a certain frequency or above a certain frequency will not transmit, depending on the modes. So we'll learn about those next time. Any questions about anything? Do you know how to solve this problem now? Okay. I'll see you next time. If you have any questions, send me an email or just come by. Thank you.